So the speed of the transverse wave is given by the formula v equals to square root of TL over m, and then we are provided with the table. We are provided with the values of the quantity along with the percentage uncertainty. So the first part is state an appropriate instrument which is used to measure the length. In our syllabus, we have 5 length measuring instruments, which include micrometer, vernier calipers, meter rule, tape measure, and trundle wheel. And for this length, we can use tape measure because it's more than 100 centimeters. So tape measure would be perfect. The next one is use the data in figure 1.1 to calculate the speed, and the answer should be in meter per second. So I mean the formula is there, the values are there, but you need to convert the units. It has to be in meter per second. So let me do the conversion first. 126 centimeter would be 1.26 meters, and 5.1 grams would be 5.1 into 10 raised power minus 3 kilograms. And then we have the formula v equals to T, which is tension 1.8 times the length is 1.26 divided by 5.1 into 10 raised power minus 3. And then square root of it. So if you hit it on the calculator as it is, you'll be getting 21.1. You can also write 21 meter per second. Either way, it would be acceptable. So the next part is use your answer in B and the data in figure 1.1 to determine the value of V. We already have the value of V along with its absolute uncertainty. And then finally, to appropriate number of significant figures. So we do have the principal value, which is 21.1, but plus minus, what is the absolute uncertainty? We need to find the absolute uncertainty. So for this one, since in the formula V, the quantities are being multiplied or divided, we'll add the percentage uncertainties. The percentage uncertainty of T, of L, of M. So for T we have how much? 5% for T, plus for length we have 1% for length, plus for mass we have 2%, but then we have the whole square root of it. So square root means raised to the power 1 over 2. And the rule says whatever the final percentage is now would be multiplied by whatever the exponent is. So this one would be 678 divided by 2 would be 4. So 4% is the percentage uncertainty of V, 4%. Now let us find 4% of this principal value. So 21.1 multiplied by 4 divided by 100. So what we get is 0.84. Now our answer is 21.1 plus minus 0.84. But then the last part is write your answer to appropriate number of significant figures. The absolute uncertainty has to be in 1 SF. That's a rule. The absolute uncertainty in A-level physics has to be in 1 SF. So I'll reduce it to 1 SF, 21.1 plus minus 0.8 We don't write 0.80. 0.80 would again be 2SF. So 21.1 plus minus 0.8 meter per second. Charge is a derived quantity. The base quantity is electric current. So then we have this question. This is the question from base units. We need to show that C has no base units. So in the first step, I can rearrange the expression for C. So let me get rid of the square root first. I can take square on both sides. And then I can take, make C squared the subject. It would look something like this. Alright, so let us now insert the units in this expression. There are different ways you can solve this. So the units of T would be second, and the unit of K. K is a spring constant. We need to find the unit of K. So spring constant equals to force per unit extension. Force is kgms minus 2. Extension is meters. Meter cancelled out. We'll be left with kg s minus 2. So for time we have second square. For spring constant we have kg s minus 2 divided by, for mass we have kilograms. Kilograms cancelled away with kilograms. S raised to the power plus 2 combines with s raised to the power minus 2. It would be s raised to the power 0, which is 1. So we are, the first part is easy. It's all about the definition. So velocity is defined as the rate of change of displacement. Acceleration is defined as the rate of change of velocity. I'll just skip this one. A car of mass 1500 kilograms travels along a straight horizontal road, and you are provided with displacement time graph. Use figure 3.1 to describe qualitatively the velocity of the car during the first 6 seconds of the motion. Give reasons for your answers. So we are provided with the displacement time graph, but we have to answer for the velocity. So if you're provided with the displacement time graph, and the gradient of this graph would give us the velocity. The gradient of this graph. If you are able to comment on the gradient, we'd be able to comment on the velocity. So let's see what happens to the gradient initially. If you have a straight line, the gradient is constant. So you see, initially the gradient is constant. Gradient represented by m. M is constant. So if the gradient is constant, we can safely say the velocity is constant initially. I mean, we can also specify the time as well, like for the, you can say for the first 2 seconds, pretty much for first 2 seconds the velocity is constant. But if you don't want to specify, we simply say initially the velocity is constant because the gradient is constant. And then what happens? This is what happens afterwards. The gradient decreases because the line becomes more and more horizontal. So gradient decreases. So gradient has now decreased, so velocity would also be decreased. Towards the end, in this part the gradient decreases. Towards the end, we once again have a straight line, which means gradient is again constant. So velocity is also constant. But then, since at 2 stages we have the constant gradient, you'll have to compare the magnitude of these two gradients. Like at what stage the gradient is greater? Is this constant gradient greater than the last one? The answer is yes, because initially the line is steeper. So towards the end, the gradient is constant, but that would be less than the initial constant gradient. So how do we phrase all of it? We break it down into 3 steps. For 3 marks. Now many of the students, uh, they don't add the last part. They don't compare the magnitude of the gradient of the initial and the final velocity. You have to include this thing. Whenever you have 2 stages where the velocity is constant, then you have to make a comparison of the value of the velocity. Like at what stage the velocity is greater or smaller, or if the two values of the velocity are constant, they are same, then you simply write it down, and the initial velocity and the final velocity are same. Anyway, let's move on to the next one, which is part 2. Calculate the average velocity during the time interval from 0 to 1.5 second. So for the average velocity, we simply have a formula. Average velocity equals to total displacement divided by the total time. So till 1.5 second, what is the total displacement? Let's find out. I can draw a straight line till 1.5 second. So 1.5 would be exactly in the middle of 1 and 2. So someplace over here. So this is a point that gives us the displacement at 1.5 second. So how much is that? So this is 40. Then this one has to be 50. 1 2 3 4. So one block would represent 2. So 42, 44, 46, 48, and then we can have 50 over here. So we are exactly in the middle of, if I could see, in the middle of these two. So 42, 44, 46. We are in the middle of 44 and 46, which is 45. So we have to be very specific with this. We have to be very careful. We cannot say this is 44 or 46. It's exactly in the middle. We can read it through the graph. So the total displacement is 45 and the total time is 1.5 second. So 45 divided by 1.5, we get 30. We write it down as it is, 30 meter per second. No other answer, by the way, no other answer is acceptable. So if you write 44 divided by 1.5, you write 46 divided by 1.5, you'll be getting the wrong answer, because in this graph you can clearly read that the point is exactly in the middle of 44 and 46. Anyway, let's move on to the next one. Show that the average acceleration between 1.5 second and 4 second is minus 7.2 meter per second square. This is a question that only few students were able to solve. So we need to find the value of the average acceleration. For this one, all we need is the two velocities, the initial velocity and the final velocity. And then we can simply use the formula of the acceleration, which is initial velocity minus final velocity. Final velocity minus initial velocity divided by the difference in the time in which the velocity changes from u to v. So let me write down the expression first. So this is the initial velocity, the velocity at 1.5 second, and this is the velocity v, the velocity at 4 seconds. Now the question is, do we have the value of velocity at 1.5 seconds? The answer is yes. We found the value of the velocity in the previous part. If I could scroll up, you can see over there, we found the value of velocity at 1.5 seconds. How much was that? It was 30 meter per second. But then the thing is, we don't have the value of the velocity at 4 seconds. So we'll first need to find the value of the velocity at 4 seconds, and then we can insert those two velocities in the formula. So how do we find the value of the velocity at 4 seconds? Through displacement time graph, by finding the gradient at that point at 4 seconds. So we'll need the ruler, and we'll draw a line exactly at 4 seconds. So this is a point that we are concerned with. So we need to find the velocity at 4 seconds. So if this point is on the straight line, which is this point is indeed on a straight line. Yeah, so this point is on the straight line. We can easily find the value of gradient of this line. So since this is a straight line, the gradient here would be the velocity, gradient here would be the velocity, gradient here would be velocity. Gradient anywhere on this straight line would be equal, hence the velocity anywhere on the line would be equal. So if I'm to find the gradient of this line, I can take 2 points. The first point would be, let me read the coordinates. The x coordinate is 4, and what is the y coordinate? One line below 100, 98. And then I can choose the last point, 1 point over here. The x coordinate is 6, and the y coordinate is 120, and then one line above 120 would be 122. So this is x1, this is y1. This is x2, and this is y2. Any 2 points could have been chosen on the line. You'll be getting the same answer. So the velocity would be 122 y2 minus y1 over x2 minus x1. So you solve this thing, you get 24 at the top, and 2 in the denominator, you'll be getting 12. So the velocity at 4 meter per second is 12. And matter of fact, the velocity is 12 in this entire region. The velocity is constant. How much is that? 12. So now we do have the value of the final velocity, or you can say the velocity at 4 seconds. We do have the value of it, which is 12 meter per second. And you see, this is consistent with the first part where we said the velocity at the end is constant, but it is less than the initial velocity. This is what we said initially. And mathematically, these two values are consistent with our statement. So let me insert the values in the formula. A equals to v minus u divided by the difference in time from 4 till 1.5 seconds would be 2.5. So we'll be left with minus 18 divided by 2.5. We get exactly 7.2 with the negative sign. Now for the last one, calculate the average force exerted. For the average force, we have the formula F resultant equals force equals to mass times the acceleration. Since the acceleration is the average acceleration, that's why they're using the word average force. So mass was given in the very first line of the question, which is 1500 times the acceleration is 7.2. Here we simply need the magnitude of the force. If you want to insert with the negative sign, either way the answer is acceptable. With the negative sign, with the positive sign. So we get a 7.2 times 1500, 10800, or in 2SF 11,000. So 2SF is also acceptable, 3SF is also acceptable, and you can write it with the positive sign or with the negative sign. Either way the answer would be acceptable. So we'll just end the first part till here and start off the remaining of the page. So this one was kind of a tricky question, especially the part B of it, in which you need to calculate the tension in the cable for 3 marks. And knowing then the acceleration up the slope is given as 0.130 meter per second square. Acceleration is not equal to the acceleration of free fall because the situation is not a free fall situation. It's not moving vertically downward or upward. So in the first part, we need to show that the component of weight of the log acting down the slope is 1070. So that's probably the easiest one. The component that is along the slope, that is down the slope, is always mg sine theta. If this is the angle theta. So mass is, it's given as 452 times the gravitational field strength times sine of the angle. So if we write it on the calculator as it is, okay, so let's get back to this one. So mg sine theta would be 1072.7 which then in 3SF can be rounded off to 1070. So let's move on to the next one. The log starts on rest. A constant friction force of 525 acts on the log. The log accelerates up the slope with the acceleration, which is given as 0.130 meter per second square. Calculate the tension in the cable. So whenever the system is accelerating, the very first equation that we write is this one. Everything else would be done afterwards. You see the word acceleration? Straight away, write down this expression. F resultant equals to ma. Among the resultant forces, or I should say among the forces, there would be a tension also. Mass is given already, acceleration is given over here. So let us label the forces in the question on the diagram. So friction is 525 and it moves up the slope. It accelerates up the slope. So that means the direction of friction would be down the slope. How much? 525 Newton. I marked one of the force. Another force is a component of weight which is down the slope, and that is mg sine theta. How much was that? 1070. Mg sine theta, it is 107. You can roll over here because mg would be vertically downward. Mg cos theta would be perpendicular to the slope. So someplace over here, this would be mg cos theta, and down the slope would be mg sine theta. So the value of this force is 1070 Newton, mg sine theta. So is there any other force? Yes, there is tension also, which would be in this direction, because this log would try to stretch the string, but the tension would try to compress it. So the tension would be to the point of connection of the cable with the motor, or you can say towards the motor, because the string, the tension in the string would try to compress the string because the log is trying to stretch it. Now, how many forces do we have? Well, we have the first force, tension. Then we have the second force, mg sine theta, which is 1070. And the third force is tension. According to the Newton's second law, F resultant equals to ma. Now, what is the resultant force? The resultant force would be the sum of the downward forces minus the sum of the upward forces, or the sum of the upward forces minus the sum of the downward forces. Upward means up the slope, downward here means down the slope. But which one of these set of forces is greater? The answer is the forces, or the force that is up the slope. How do we know? The force up the slope is greater. That's the only reason why the log is moving upward. That's why it's accelerating upward. So the force is up the slope minus the forces down the slope, which include the friction, plus mg sine theta. In all of it equals ma. Now, what is the tension? Well, we don't know. We need to find the value of tension minus, what is the friction? 525. plus what is mg sine theta? The all of it, mg sine theta is 1070. That equals to ma. M is 425. Acceleration in this case is not 9.81. I repeat, it is not a situation of free fall. It's not a vertical motion. So the acceleration is, matter of fact, given in the question itself, 0.130. So we solve the right side. We add these two. This thing is being subtracted on the left side. On the right side, all of it would be added. And if you solve for the value of tension, you can do the mathematics from here. The value of tension in 3SF would be 1650. The log is initially at rest. Initial velocity is 0. It is pulled through a distance of 10 meters. Distance or displacement, you can say, is 10 meters because it's being pulled in a straight line. So these are essentially the same. Calculate for the log the time taken to move from S to P. So speed equals to, or velocity equals to, displacement over time, and then time equals to S over V. We can absolutely not use this one. Absolutely no for this expression. Why? Because the thing is, the system is not moving with a uniform velocity, rather it is accelerating. Whenever the object is accelerating, we can never use this expression. What do we use then? Well, we have these set of equations. We can use any of it. I mean, depending on the situation, what kind of data do we have? So we don't have the final velocity, so I can't really use the first one. I can indeed use the second one because the displacement is given as 10. Ut would, all of it would be 0 because the initial velocity is 0. 1 over 2 as it is. It's not the free fall, so the acceleration would not be minus 9.81 with the convention. No, it's not the free fall case. The acceleration was 0.130 times t square, and then you can simply get rid of this thing. Plus 0 doesn't make any difference. So 10 times 2 would be 20 divided by 0.130, and then you take square root of this thing, and thereby you get the value of t, which I assume is 12.4 seconds, or in 2SF12. Calculate the magnitude of the velocity at P from S to P. The velocity at S is initial, the velocity at P is final, so we need to find the final velocity. So what if I use the first equation or the third? You can use either of it because you do have the value of time as well. So v square equals to 0 square plus 2. Acceleration would be this much, and the distance or the displacement is 10. You hit it on the calculator. Plus 0 won't make any difference, so it's not even there. Then you take square root on both sides. You'll be left with 1.61. Now the most important one, part C. The cable breaks when the log reaches a point P. On figure 2.2, sketch the variation of the velocity with respect to time. So the graph should show velocity from the start and S until the log returns back to the S. But the only situation, the change is this one. Now the cable breaks when the log reaches a point P. So this is the situation that we have. When the log reaches a point P, cable breaks. So initially, at the start, the motion. Let's talk about the motion. It is at the point S. This is the start point. It goes to the point P then. Cable breaks at the point P. And then it rolls down towards the point. So as the ball speeds up from 0 meter per second to whatever the velocity was, the velocity would increase because the initial velocity was 0 and the velocity at Q was 0, but the velocity at P was 1.61. Sorry, at S the velocity was 0, at P the velocity is 1.61. So it speeds up with a constant acceleration or uniform acceleration. How much is that acceleration? 0.130. It speeds up with that acceleration, uniform acceleration. Then what happens? As the cable is broken, there won't be any force which would increase the speed of the log further. So as the cable is broken, now the logs would start to slow down and its velocity would be reduced to 0 once again. So what does that look like? The log goes till this point and then the cable is broken. So there is no tension, there is no forward force, there is no force by the motor to move it upward. So its speed would decrease and decrease and it would be eventually reduced to 0, probably as it reaches this point. It'll move like probably 2-3 meters due to the momentum, due to the inertia. It continue the motion, but eventually his speed, as it is moving, its speed would slow down and eventually would be reduced to 0. So the object would start to decelerate with uniform deceleration, but at the same time that deceleration magnitude wise that deceleration would be greater than the initial acceleration. So two things here. Now we have uniform deceleration. But this uniform deceleration, the magnitude wise, it is greater than the initial acceleration. How do we know this? Well, you can get back to the expression. The easiest way would be to explain through the expression. You see, acceleration was A equals to, if I rearrange for acceleration, T minus F plus mg sine theta divided by mass. This is what the expression for acceleration is. So this is the acceleration when the tension was there, when the cable was there. So T minus something. So we do have the value of this also, by the way. And the acceleration was 0.130. If tension is not there, what is the new value of acceleration? It would simply be F plus mg sine theta divided by mass. And which in this case, this value would be greater than the previous one. I mean, mathematically, it is very clear. Even without inserting the values, we can make a quantitative analysis or even a qualitative analysis, because in the second one, these two terms are being added and they are not being subtracted from anything. But if you try to find the acceleration, I mean, friction was 525 plus this force was mg sine theta was 1070 divided by mass is 452. And then if I hit it on the calculator, this acceleration is 3.52. So which is technically the deceleration. So the magnitude of the deceleration is greater than the magnitude of acceleration. Hence, the line of the deceleration would be steeper. This one would be steeper because the magnitude of deceleration is greater than the magnitude of acceleration. What happens afterwards? After that, it reverses the direction momentarily. The log would be stopped. I mean, the log goes from here, crosses this point, the cable breaks, probably reaches this point, stops to 0, and then it starts to roll backward. Now it has to cover distance more than 10 meters. So its speed would be greater than the previous velocity, 1.61, but with the opposite direction. But the acceleration would be same. Now the acceleration would still be 3.5 something, whatever it was. So now it looks something like this. So what happens at this point? The velocity reverses, final velocity greater than 1.6, the magnitude of final velocity. the magnitude of the final velocity is greater than 1.61 meter per second.